webinar introduced by Professor Elias. Professor Elias is or serves as a computer science professor and director of the Computer Algebra Research Group of Wilfrid Laurier University. He also has over 150 referred journal and conference publications, chapters in books, edited books, and special issues of journals in the research areas of computational algebra, meta-heuristic, high-performance computing, dynamical systems, and the combinatorial design theory. He served on the editorial board of 7 international journals. He also served as managing editor of two Springer journals and as editor-in-chief of Springer journals and a pre-course book series. He has organized a very large number of international conferences in Europe, North America, and Asia, often serving as a committee or program committee chair or general chair. His research work has uh, approximately 1,200 citations. He also served as chair of the ACM Special Interest Group on Simple Computation. Also, he is a co-chair of the Applications of Computer Algebra Working Group and has delivered over 20 plenary invited talks about the world. So, Professor Elias today he will give us a talk about big data and combinatorics. So the talk it will be 45 minutes, and after that, if you have a question, you can ask question to Professor Arias. So we thank you very much for Professor Arias, so he can begin the talk.
Okay, thank you, Ahmed, for this nice introduction. Is the sound okay?
Yes.
Yes, okay. I shared my screen, so hopefully, thank you, Marvin. So hopefully you can see my screen, the overheads, and so I can start right away if everything is fine.
Can you share your screen one more time? I think it might be down for the moment.
Okay, yeah, so let me try that again, sorry. Okay, now?
Perfect, yeah.
Okay, all right. Sorry about that. Okay, Eric says can't see the screen. Okay, now it's good. All right, thank you again, Ahmed and Kerry, for organizing this online seminar. My title today is Data and Combinatorics. I'm very grateful to all of you for being here. So I want to start with some line of what this talk is about. There are two parts. The first part is some sort of introduction to this combinatorial area that I work on for the past 15 years, something like that. It's a very large area, engineering applications, of course. And the second part of the talk has to do with the big data problem, or one big data problem that arises naturally in this research area. I want to explain it and also give some background on what unsuccessful attempts or successful attempts, depending how you see it, we have been able to use so far in the study of this big data problem. So to start, I want to mention the concept of periodic and aperiodic autocorrelation of finite sequences, which is used to define the complementary sequences. Then I want to talk a little bit about compression of complementary sequences, and then mention that this periodic and aperiodic autocorrelation is important because it can be used to give a unified description of dozens of combinatorial objects, Hadamard matrices, the optimal matrices, weighing matrices, and so on. Briefly, I will touch on some alternative formulations, including matrix, polynomial, algebraic, and more importantly, perhaps for this audience, combinatorial optimization formulations. So let's get started with this introduction. Correlation of finite sequences is a very simple concept. You start with a sequence capital A with n elements a0, an minus 1. The periodic autocorrelation is defined by this sum over here, where k goes from 0 to n minus 1, ak plus s, where obviously the index k plus s is taken modulo n, so that we're still within the indexing scheme of the sequence from 0 to n minus 1. This is the periodic autocorrelation function, and so these coefficients are defined for every s from 0 to n minus 1. Obviously, PAS of 0 is just the sum of the squares of the elements of the sequence. PA1, if you like, is the idea that you take your sequence, you shift it by 1 to the right in a cyclic manner, and then you take the inner product of the original sequence and shifted sequence. There is a sister concept of periodic autocorrelation function, which is sort of the same, but now we don't do the shift in a cyclic manner. We just chop off the remaining elements of the sequence when we do the shift, and then we take the product. And that is this definition NAS, the sum from k from 0 to n minus 1 minus s, ak plus s. Let me give you an example. So for n equals 7, if your sequence is labeled A0, A1, A7, or 0, A1, A6, these are pretty much equivalent, then this is how the periodic autocorrelation coefficients look like above, and this is how the aperiodic autocorrelation coefficients look like at the bottom. So basically, periodic autocorrelation has a constant number of quadratic terms. Aperiodic autocorrelation has a decreasing number of quadratic terms. So NA is just one quadratic term, the product A1 times A7. And if you look at this table, this example of values, this table of values of PA and NA, periodic and aperiodic autocorrelations, then you notice that, first of all, P6 is equal to PA1, PA5 is equal to PA2, and PA4 is equal to PA3, and this is a well-known symmetry property. Basically, half of the periodic autocorrelation coefficients are equal to the other. And also, you notice that if you take the sum of NA6 and NA1, you obtain PA1, and this is a general property which is recorded here at the bottom of this slide. PAS is equal to NAS plus NA times N minus S, and this is true for every S, including, I guess, for S equals 0, which is a trivial case. But in any case, it is true for every S from 1 up to N minus 1, where N is the length of the sequence. So another important ingredient in all of this area is the circulant matrices. The circulant matrix CA is shown here. You see that the first row is A0, A1, AN minus 1. The second row is a right cyclic shift by 1 of the first row, and so on and so forth. So every row is a right cyclic shift of the previous row. So that means that circulant matrices are important because we sort of know a circulant matrix with a linear amount of indeterminates, the elements of the first row. We don't need to know square elements for an n by n matrix, general n by n matrix. For circulant matrices, we need big O of n elements to know the entire matrix. What is the connection between circulant and circulant matrices and periodic autocorrelation? Well, periodic autocorrelation is the inner product of the row over circulant matrix and the I+1 row for every I. So this is important because it gives us a matrix form of periodic autocorrelation. And also, a few years ago, 7 years ago, I contributed a chapter on the Handbook of Combinatorial Optimization, the second edition, edited Pardalos, Du, and Ron Graham, where I sort of put forward this idea that one of the reasons that the correlation is important is that it gives us a means to offer a unified description of combinatorial objects. And to be more specific, what I mean by that is that we can look at this table here on slide 7. This table has 3 columns. Column is the number or type of sequences. The second column is the defining property, and the third column is the name of the combinatorial object. For example, if you look at, let's say, Golay sequences, which are very famous sequences defined by this telecommunications engineer Marcel Golay in his famous IEEE transaction information theory series of papers. If we have 2 binary sequences, by binary we mean with the elements plus and minus 1, and if periodic autocorrelation coefficients, the corresponding periodic autocorrelation coefficients of these 2 binary sequences sum to 0, then these are called Golay sequences. If we change the aperiodic to periodic, so we have 2 binary sequences, but now the periodic autocorrelation coefficients sum to 0, then these are Hadamard matrices, and so on and so forth. This table should have been a lot bigger, but I just wanted to fit a part of it in a slide. The main idea here is that the concept of autocorrelation serves to give a unified description of dozens of different combinatorial objects. So what do we mean by complementary sequences? Golay sequences are one special case for a periodic autocorrelation. We mean that if we have, let's say, T sequences of length V with complex elements in general, then if we compute the periodic autocorrelation function values and we take the sum of the corresponding values, and if this sum is a constant alpha, then these are called complementary sequences. I want to show you an example. This is in Maple, and of course, when you work in Waterloo, okay, you have to use Maple, right? MapleSoft, the company that makes and distributes Maple, is based in Waterloo. So this AA here is a sequence of 50 plus and minus ones, and BB is another sequence of 50 plus and minus ones. This is my here of the PAF, the Maple definition of the periodic autocorrelation function. So the sequences AA and BB have 50 elements, binary elements, each one. And now I compute the periodic autocorrelation function coefficients for AA, and I get these values 2, 2, minus 2, 2, minus 2, minus 2, 6, etc. And just underneath, I compute the periodic autocorrelation function values for the BB sequence, and I get minus 2, minus 2, 2, minus 2, 2, 6, etc. So you notice that if you sum these 25 numbers vertically, then you get 0 everywhere. You get 25 zeros. This is an example of a complementary sequence, and example of again complementary sequence of length 202. Now A is a sequence with 202 elements, and B is a sequence with 202 elements. And if we play the same game, then we can compute the 101 periodic autocorrelation function values and sum them up, and we get again 101 zeros. In other words, we just solved a system of quadratic polynomial equations with 100 equations and 402 binary variables. which seems like an impossible task, and it is doable using various combinatorial methods. I will these things. I just want to say here that searching for complementary sequences amounts to searching for needles in haystacks. And these are Claude Monet famous haystacks. And this is the Chinese version of this proverb, the needles in a haystack. So if there are any Chinese speakers in the audience, then you know what this Chinese proverb at the bottom. So let me skip a couple of things in the interest of time. Let me skip a few. I just want to show you a numerical example just to make some of these things more precise. So this example here is the same example that we had before. And while in the previous example, we illustrated the autocorrelation function invariant, if you like. So the sum of the periodic autocorrelation constants is 0. Now I illustrate a second invariant, which is the invariant of the power spectral density, or PSD. And the power spectral density is the squared magnitude of the DFT of this sequence, the usual DFT, the discrete Fourier transform of the sequences A and B. So if we compute for the first value of S, so S equals 1, we compute the PSD value of the A sequence, and this is 87.0, etc. Then we compute the PSD value for the B sequence, and this is equal to 12, 4, and so on. And if we add these two values together, then we obtain exactly 100, which is 2 times 50, 2 times the length of the sequence. We do the same for every S up to 24, and it turns out that in all cases, when we compute the sum of the PSD of A and B, then we get 100. So this is the Again, the PSD values are simply the square magnitudes of the discrete transform elements associated to the sequences A and B. And that brings me to the next sort of main concept in this area, which is the concept of compression. So what we do in compression is that we have the following. We have a sequence A0, A1, AB minus 1. The length V is a composite number, let's say D times M. So if V is a prime, then this compression business doesn't work. But if it's not a prime, if there is a non-trivial factorization D times N, then we define these subsums AJ A underscript J upper script D, which are defined like this, and we take the sequence of all of those. This is a sequence of length, and this is the M compression of A. An example below, this CW249. CW24 is a circulant weighing matrix with length 24 and weight 9. The weight is the number of non-zero elements. So you notice that you have 0 elements, 9 plus and minus 1 elements, and the rest of the 24 elements are 0. 24 has plenty of divisors. So for M equals 2 equals 12, this sequence of order 12 is the 2 of the CW249. And this other sequence with M equals 3 and D equals 8 is the compression of the 3 compression of this CW249. And is this compression important? Because we have a theorem from 2012 with my collaborator and mentor in design theory, Professor Djokovic. If we have T complementary sequences like before, then and if the length V is a composite number, then we can compress all these sequences simultaneously. And then the set of compressed sequences AID from I from 1 to T is also complementary. And moreover, we give the exact value of the constant for the periodic autocorrelation function invariant. That is M times alpha, where the compression factor and alpha is the original periodic autocorrelation function constant. And for the PSD invariance, we have the property that the PSD constant remains the same, this constant beta, for the compressed sequences. And using this techniques, we were able to find, for instance, periodic Golay pairs of length 68. You can see all of the combinatorial constraints here. And what we did is that we used two compression. So we found the sequences A34 and B34, which are these listed up here. And I will skip some of the consequences, the combinatorial details, and just mention this was in a paper in 2015 in Discrete Applied Mathematics. And this is A and B, with where the plus and the minus given with this constant encoding, the minus and the plus. And this periodic Golay pair of length 68 allows us to compute to construct Hadamard matrices of order 2 times 68. Then we went ahead with another length, even harder, the length 72. And in that one, we used again several 72 is divided by 3. So we used 3 compression, and in this paper in 2015 from a conference in Alberta, we constructed periodic Golay pairs of length 72. The issue here is that this is a very cumbersome and it took also pretty much generating 10 million lines of C code using metaprogramming and Maple and other Linux tools and so on. It is doable, but it's a very cumbersome process. The next open case for periodic Golay pairs is the order 90. And we believe that they exist, but well, no one knows how to find an example. So skip some of the formulations and go to the optimization formulation of these problems, which may be more interesting to some of you in the audience. So how do we search for complementary sequences using an optimization formalism? Well, you know that we have to write an expression like this: minimize x transpose A times x, where x belongs to the Boolean cube 0, 1 to the n. And well, how can we? Well, we can transform the periodic autocorrelation function into some symmetric matrices Mi, which are defined like this. The element mjk is equal to mkj is equal to 1/2 for technical reasons, when the monomial ajak appears in the expression of the periodic autocorrelation at I, and mjk is 0 otherwise. So these matrices, with these matrices, we can transform the problem for searching for complementary sequences to a combinatorial optimization problem. And this is an example for n equals 8. You can see how these matrices look like. There are 4 of them, 4 symmetric matrices in red on the. And the reformulation of the problem of finding complementary sequences with periodic autocorrelation function equal to 2 is find 2 binary sequences A, B such that A transpose MI A and B transpose MI B is equal to 2. And this is a problem that can be tackled with combinatorial optimization algorithms. I'm going to skip a few things. I see that the time is of the essence. I just want to mention a couple of things on the meta-heuristic approaches to these problems. So for heuristic approaches, you need an objective function, first of all, and there are many ways to write an objective function, is either as the sum of the squares or as a sum of absolute values, which is not a smooth function, but you can still optimize it with meta-heuristic algorithms like genetic algorithms, particle swarm optimization, and colony optimization, and so on. The problem with all these approaches, they suffer from the same problem. In this combinatorial problems that we're looking at, there are several trillions of local minima. And therefore, this is a picture of an objective function landscape. You see the zeros in clusters at the bottom on the x-axis, and then you see the spikes, which are the other values of the objective function. So this is why these kind of problems are difficult. There are many interactions with coding theory, some open problems listed in this Grosvenor basis coding and cryptography. There is a lot of interactions with information security and coding theory, of course, and again, there is a NATO volume by two very well-known combinatorial mathematicians and coding theorists in 2011. And now I want to briefly discuss Hadamard matrices, and these are some of my favorite references: the book on Hadamard matrices by Adam, the Handbook of Combinatorial Designs by Colburn and Dinich, and the book Combinatorial Designs Constructional Analysis by Doug Stinson. So a Hadamard matrix is an n by n matrix with plus and minus elements, so that if you multiply the matrix with its transpose, H times H transpose, then you get n times IN matrix. So if you scale these matrices by 1 over square root of n, obviously these are orthogonal matrices. So Hadamard matrices are like orthogonal matrices, but not exactly 1. There are trivial cases when the dimension is 1 and 2, and then there is a well-known necessary condition for the existence of this matrix. If a Hadamard matrix exists, then the order must be a 0 multiple 4. The order of a Hadamard matrix must be a multiple of 4 outside the trivial cases 1 and 2. Now the sufficiency condition is the famous Hadamard conjecture, which is one of the hardest problems in design theory. It says specifically that there exists a Hadamard matrix of order n for every n which is a multiple of 4. And this is open since 1893. Until 1985, the smallest unresolved order was 268. I have some other important resources here for Hadamard matrices and relational computational methods, starting with the book by Guang Gong and Solomon Golay from the Viterbi School of Engineering in California, and also the book by Orthogonal Designs by Jennifer Siberry, and also the book by Kreher and Stinson on combinatorial algorithms. So I also want to mention that we started about 5 years ago with Curtis Bright, who is currently in Ottawa, Vijay Ganesh at the University of Waterloo, and myself, their collaborators. This can you hear?
Yes.
Yes, we hear you.
Okay. Someone wrote no audio on the chat. Okay, good. Then I will continue on. So this project is called MathCheck. It is a system that we developed with these collaborators using concepts from Boolean satisfiers, or SAT solvers, and combining the power of SAT solvers with the power of computer algebra systems in order to verify conjectures in mathematics and look for counterexamples. So, and the smallest unresolved order of Hadamard matrices up to 2004 was 428, and currently, as of today, in 2020, the smallest unresolved order is the order 668. In other words, nobody knows whether or not a Hadamard matrix of order 668 exists, but everybody suspects that there is one. We had a new result in 2012 in this paper in JCD, the Journal of Combinatorial Designs. We constructed a matrix of order 4251, which is a prime, the 251, and the tools that we used are related to this big data approach that I want to discuss in the second of my talk. There are also some interactions with quantum computing. So weighing matrices are generalizations of Hadamard matrices. They have this property W transpose is equal to K times IN. So if K is equal to N, these are Hadamard matrices. K can be anything from 1 to 2 to N minus 4. These are used in this paper in Journal of Physics 8 and algorithmic papers by well-known researchers in quantum computing. So let me go into the second part of my talk, which now introduces the big data problem that I want to tell you about. And this big data problem has to do with matching. And I want to discuss the approach that we tried so far, namely the meet-in-the-middle approach, hash functions for parallel collision detection, parallel backtracking, the bins approach, and the last digit or some other hash function approach. So two-way matching is the following. The input of this problem is a positive integer constant lambda, and two files A and B, like text files A and B, with k columns and n rows, positive integer elements. And the output is what we call a match. And by output, we mean find two line numbers, LA and LB, one in file A, one in B, so that LA1 plus LB1 is equal to lambda, and all the way to the kth column, LAK plus K is equal to lambda. I want to illustrate this with an example to make it easier. So if this is file A with these 4 lines and file B, other 4 lines, and lambda is 100, k equals to 3 columns, n equals 4 rows per file, then LA is 2 and LB is 3. In other words, if we take the second line and we add it to the third line, the second line from file A and the third from file B, then we get 100 all the way through. We get 100 3 times over. So this is like a vector, again, a vector version of the two-sum problem. And the issue here is that typically lambda is a large number, 3-digit number. The elements are maybe of the size up to 100. K can be in the range from 40 to 50. So we have 40 up to 50 columns. And of these files can be into the terabytes. So n, the number of rows in A and B, which by the way can be different. The number of columns is the same, but the number of rows can be different. So n is in the several millions. We need this problem. Why do we need to solve it? Because it allows us to, using all these techniques that I told you, it allows us to find solutions for the optimal matrices, Hadamard matrices, weighing matrices, etc. And now I want to find two other versions of this problem, which are significantly harder, the three-way matching and the four-way matching. And these are on this overhead 39 as follows. Suppose that we now have 3 files, A, B, C, and again we have constant lambda, we have k columns and n rows per file. Then we're looking for 3 line numbers, LA, LB, LC, in the files A, B, C respectively, so that the 3 sums, LA1 plus LB1 plus LC1 is lambda, and all the way to the kth column, LAK, LBK plus LCK is equal to lambda. And in four-way matching, we have, the K and N, the same parameters, and 4 files A, B, C, D. And now the match is 4 line numbers, LA, LB, LC, LD, in files A, B, C, D, so that the corresponding 4 sums, K corresponding 4 sums, are all equal to lambda. And while we know how to solve this problem. Let me go back here. The two-way matching problem, we know how to solve it up to terabytes instead of in terms of file sizes. For three-way and four-way matching, we are stuck when the files ABC contain, let's say, 10 million lines each one. Okay, that's the. So I want in the remainder of the talk. I'm sorry, I'm taking a little bit extra time. I want in the remainder of the approaches that we have tried so far, which are satisfactory in some sense, but also not satisfactory. We still need some through algorithm in these problems. And again, in the 3 and 4 matching, the two-way matching is doable. We can do it, no problem. But the 3 and 4-way matching hard. So the first thing that we tried back in 2014 in this paper in the Journal of Combinatorial Designs, where we were able to find this open order Hadamard matrices of order 4 times 251, was a classical meet-in-the-middle approach in amortized time being A2, A3, A4, where A1, A2, 4 answer something on the chat. Thank you, Asit, for your question. So if we have 4 files, A1, A2, A3, A4, then this is the amortized complexity of this approach, basically hashing two sums from 2 files and then the difference from the other 2 files using some complicated 64-bit hash function. And so you can look up more on this paper cited, this 2014 paper. Then we tried the collision search approach. The algorithm that we used is this January 1999 paper from the Journal of Cryptology. What these two cryptographers that at that point worked for Nortel Networks, what they did is that they a parallel approach to find collisions on hash functions. So 2 inputs x and y, which are different, but they have the same value for f, the hash function. This is a collision. And what they do is that they sort of have these distinguished points, and then they define these that run from various areas in the search space. And every processor following one of these trails, and if these 2 of these trails are merged, then this is a collision. So adapting this approach, we published a paper in 2015 with Professor Djokovic and a master's from the Institute of Quantum Computing, Olivia Di Matteo, where we found new symmetric Hadamard matrices of these orders. Then another approach that we tried is the parallel backtracking approach. This was done by a student in the Cargo lab, Ian Lee, in 2015. So his approach was to use a standard parallel backtracking algorithm. For example, the one found in this reference by Roger Labby, and also ideas from the book, well-known book in the literature by Judea, 1984. And Ian put together his code and tested it on 5 different supercomputers, which are listed here: the BGQ, Graham, Niagara, Cedar, and MP2, all of them in Ontario and Quebec. A typical sample problem requires running about 2,000 jobs in this scenario, and there are very non-load balancing issues in parallelizing this approach correctly. This is a sample that he was able to solve. So A has 3 million rows, B has 80 million, C has 84 million, and D has again 84 million. So that is doable with his approach. Then we tried another idea, the idea of the bins. Again, 3 and 4-way matching. The 2-way matching is sort of trivial, but the 3 and the 4-way matching are not trivial problems to solve. Your input is gigabytes or terabytes. So this is really a very difficult big data problem, and we could use some new ideas. So for the bins approach, the main idea is to consider the first column and create that contains the line with the same number. And it turns out, because of the underlying distribution of these numbers, it turns out the resulting distribution of the sizes of the bins looks like a Gaussian. So this is not, of course, accidental, right? It can be studied further and exploited. Then you use the first constraint, the fact that the first element of a subsum is equal to lambda, that can have only a very small number of values. So you can split the problem into subproblems and recursively do the same in the second column and so forth. This requires some intricate programming, and we used this in a paper in 2016 to define difference families, some certain combinatorial designs for primes 3 mod 4, which are very important again in the search for Hadamard matrices. And the last digit approach is the idea that you can actually retain only the last digit of every number in files, which means that you apply the mod 10 hash function to your input. That can be done very fast as a phase, for example, using awk in Linux. And then lambda, the constant, you have to realize lambda is not taken mod n, because you have to account for possible carry digits in this approach. The advantages is that you get smaller file sizes. There is a constant number of bins, 10 for every file. So if you have 3 files, then you have 10 times 10 times 10 possibilities maximum. 1,000 possibilities for the subproblems. The disadvantage of doing this hashing approach is that you can introduce pseudo matches. So matches that when they are lifted from the mod 10 data to the actual data, they are not real matches. But experimentally, we've seen that the possibility of pseudo matches is 0. So this is not an issue when you have k equals 40 to 50. For example, which is a typical size for the columns of these input files. This is an example of the Gaussian distribution I was telling you. This is from a real problem where we split the problem with 600 into 674 cases, and these can be treated in parallel. The first column, 7, 44, and so on, is the number of the file A that start with 70. So 7 lines start with 70, 44 lines start with 71, 300 lines start with 72, 11 million lines start with 84 in the middle of the first column, right? So the values, the more popular are 82, 83, 84, 85, 86, 87. The same distribution, kind of distribution, appears in file B and file C. That, I mean, when I say Gaussian, if you see the first columns in each one of the 3 parts of this overhead, you realize that they can be modeled by a Gaussian. There's no doubt. It's 1:46, so I think my time is up, and actually this is my last overhead. So I just wanted to summarize and say that I hope I gave you some idea in 40 minutes of what this big data problem that we are facing is, and I hope I gave you some idea of uh, uh, what approaches are we have tried so far. And of course, the seminar is that if some of you have some ideas on how to solve this problem, this 3-way matching and 4-way matching, then of course we welcome any feedback that you might have on the algorithmic front. So I think that's it. I'm finished, and I'm happy to take any questions.
Okay, thanks, Professor Arias. So if anyone has a question, he can ask on the chat, and Professor Arias, he will respond to the questions.
Hello, thank you very much. It's Kesser here. Can you hear me?
Yes, sir. Thank you.
Sir, I am from IEEE CS chapter from RIFA International, Pakistan. Sir, my question is, you have shared some methods about the combinatorials about big data. But sir, for the beginners, can you let us know about some course, or like if I gonna start about big data, so where from I should start, like for initial beginners? Thank you, sir.
Yeah, if I understood correctly, your question is you're asking about some big data techniques, right? Did I get it right? Is this your question? Maybe if you could type it on the chat, that would be easier. Um,
Elias, feel free to answer the questions just speaking.
oh,
You can read
okay.
them and then
Yes.
answer them.
All right. Thank you, Kerry. Yes. So I see a couple of questions that sort of converging on the same theme, which is libraries, software libraries, and courses for beginners. And as I wrote on the chat, these problems are not something that the existing data science libraries, like TensorFlow is a well-known Google library, right? And toolbox, if you like. So it's not going to do anything in this problem. Then things like Amazon EC2, Elastic Cloud. Again, I don't think it's something will work right away in this problem. Now I see a question from Jakub, a colleague who is using software to find perfect or near perfect. Yes, there are similarities, definitely. Some of these codes are based, for example, in autocorrelation properties. For example, there is this OOC codes, optical orthogonal, and those are very well studied in the IEEE literature. There are dozens of papers in the IEEE transactions on information theory on OOC codes, using all kinds of constructions, bounds, recursive constructions, algebraic constructions, and so on. There is a famous paper by Fan Chung and Javad Salehi in IEEE transaction information theory, I think in late 80s or something like that, that is a reference work for optical orthogonal codes until today, pretty much. And there are, again, dozens of papers on C codes. And if you look at the definition of an optical orthogonal code, it is based on autocorrelation and on cross correlation. So the code words have to satisfy some autocorrelation property and some cross correlation property. So yeah, this is very related, and all the technologies that we developed in our on our can be used to look for optical orthogonal codes, and in fact we have some recent some ongoing paper now with some from Vancouver. We have some work where we're trying to construct optical orthogonal codes using autocorrelation properties.
Hello?
Yes?
Yes, this is Alvin. I think there was a question that I saw in a chat regarding about perhaps speaking about some of the real world practical applications of your work.
Yeah. I mentioned, various papers. For example, the quantum computing. If I can go back here, you can still see my overheads, right? So in quantum computing, I'm not an expert in quantum computing. I just know these two papers and many other ones where quantum computing researchers are using weighing matrices of various kinds. The weighing matrices is a very big topic, right? Do easily another seminar on just on weighing matrices. So they use them in quantum computing in these two papers. I would just probably say, to consult these two papers and see what they're doing. I can't tell you a lot more about weighing matrices in this context of quantum computing. On the other hand, another major application I think is related to cryptography. So the idea is that you can actually design some sort of crypto system based on this hard combinatorial problem. Sorry, the screen. Let me share it again. Is it back now, the screen?
Yes.
Thank you. So I was saying that in crypto you can imagine a crypto system that is based on this hard combinatorial problem instead of, let's say, factorization. RSA is based on factorization, right? Now NIST designing the post-quantum cryptography protocols and so on. I'm seeing another question by Tim. What are the advantages of using Maple? Well, I can definitely comment on that. I use Maple mainly as a prototyping tool. So that means I write, if I want to sort of implement an algorithm, then I can do it in 20 lines in Maple. I can do it in 20 lines in Maple instead of writing cumbersome C code or Java or C++ or whatever. Then when I get it to work, debugging and so on, then I can translate it into a more efficient language for computations and ultimately for parallelization. Because in these parallel clusters that I showed you, the only available languages are C, C++, Fortran, and maybe Python, maybe, not always. So I use it for prototyping, and also I use it for metaprogramming, which means that if you want to produce, if you're solving a problem and at some point you want to go on production mode, generate a lot of C code without bugs and so on. One way that I found how to do that is to use metaprogramming using Maple. You can email me if you like, and I'm happy to share more information. I'm not aware of any Stack like Stack Exchange. Yes, I'm not aware of any such community.
Okay, we would like to thank you, Professor Elias, for. Okay, let's have this last question.
Yeah, of course, of course.
Okay, this is Usama Ali. For how big company manages its data, like
How big company manage they? Well, they use definitely high performance computing. This is a certainty, absolute certainty. For example, Google is known for using high performance computing for large cluster for many years to manage uh, uh, the search requests online and so on, and to implement the page rank algorithm, for instance. Yeah, exactly. Alvin, right. Mhm. And there is also the Amazon Web Services or the Elastic Cloud, EC2.
Okay, I would like to thank you, Professor Elias, for the talk. And if you have any question, you can send the email to Professor Elias about it.
Yeah, of course.
Yes.
And thank you, Ahmed. Thank you, Kerry, and thank everyone for.
Yeah, and also we thank Kerry for hosting this event and for his support with us. And I hope all enjoy this talk, and we continue to do some talks also in the near future.
Yeah. So same time tomorrow.
Not tomorrow.
Same time tomorrow.
Not tomorrow. Next, maybe next. Yeah, it has to be maybe by next month. We'll do another one.
Of course, Ahmed. Yeah.
Yes. Okay. Thank you very much for you,
Thank
Professor
you.
Kerry, and for all people who already joined us for this.
Thank you.